Okay, so this is session number 8 for work power energy for us. So we'll be learning some critical new things in this session, but let's start by working on few examples of conservation of energy and application of work energy theorem first. So let us start with an example where we will utilize number of things, including constraint relations. So we have this kind of a situation now. We have a light pulley but that is connected via a spring like this of spring constant K, and there is a thread which is connected between the floor on one side going around the pulley and connected to a block on the other side. Okay. So it's an ideal spring which is connected, which is massless, okay, and it is connected to the axle of the pulley, or rather it suspends the pulley via the axle from the ceiling. Yes, okay. There's a block of certain mass like this, okay. So this system, so given that the ideal spring has a spring constant of, let's say, 50 newtons per centimeter, okay, and the pulley is of course massless, and smooth, of course, that too. The mass of the block is, let us say, 7.5 kilograms, and G is 10 meters per second square. Okay, so now initially the block is held with the in such a position that the spring is at the natural length, or the spring is in relaxed state, but the thread is just about taut, okay, and is released from rest from that position. So initially the block is being held such that the spring is in relaxed state and the thread is just about taut. Okay. So it doesn't have any tension, but at the same time it's not exactly loose. It's just about taut. Okay. So now the block is released from rest. So first of all, we want to find the block's speed as a function of its downward displacement. Okay, we want to find its speed v as a function of its downward displacement. Let's say s. We will denote the downward displacement as s. So you can start with this, and next up what we'll do is we'll find the, in due course as the block moves, we'll find the maximum speed the block achieves, and we'll find the maximum displacement that the block makes. Okay. So anyhow, just try this out, people. let's start with this example and just try to see how you can set up the work energy equation here. Okay, so let's try and set up the application of work energy here. What would be the easiest way to make use of the work energy theorem? Let's try to understand that. So as always, the first thing you need to consider. Okay, good, Kevin. I will verify your answer in just a moment. Okay, yeah, V square will be something like that. That's correct. So as always, the first thing that you need to do when you start applying the work energy theorem for a particular question is you need to decide what is your system, and therefore what is your statement of work energy theorem going to be. So let us apply for application of work energy theorem. Let us take our system as something that includes gravity and the spring. Then we can apply conservation of mechanical energy. The system is the block plus the thread plus the pulley plus the spring plus the gravitational field of the earth. If we take that as a system, then what will happen? That work done by any external forces is zero, because only external forces are like the forces acting through the clamp of the pulley and things like that, which are not doing any work. Okay, and there are no non-conservative forces because obviously we're not considering any air resistance type of force over here. So these two things happen. So first of all, this simplifies the situation. Okay, Aman, so I'm just in the process of verifying. The form of the equation is correct that you have sent. Okay. I'll just have to verify the values. Okay. So now let us see how we will apply work energy. So one thing that becomes very important over here next is the constraint relation. So how the constraint relation becomes important, let's understand this. Okay, Karen, understood. Okay. So the constraint relation becomes important like this, that the relation between the state of the spring and the displacement of the block, that is going to be an important constraint to consider over here. Okay. And to understand that constraint, we will make use of both the things. The geometrical method we can make use of, or we can make use of virtual power. Let's say a block starts from this position, and when it starts from this position, this is at natural length, speed is 0. Okay. So now the moment this system starts moving, so next up what we'll see is that after some time, so this was the situation at t equal to 0. Now at some new time, let's say t equal to t, what is happening is that okay, something like this has happened now. So our spring has got stretched by x, because what we'll have to consider is that the pulley has made a displacement of x. Okay. So as a result of that, what we'll also understand is that the block would have made a displacement. Okay. What we'll understand is that the block would have made a displacement of 2x. Okay, that is the important thing to understand here. So how do we know that? We will know that by just considering thread length. You can see that if the pulley shifts by x, it will release 2x amount of thread. So the block would have shifted down s will be equal to 2x. That is our first equation. This is a constraint relation. So this becomes something very important over here. Okay. Next, of course, we will also apply work energy theorem. So, an application of work energy theorem, we can see that change in kinetic energy of the block plus change in gravitational potential energy of the block plus change in elastic potential energy of the spring should be zero. So this is a statement of work energy theorem. This is how we are able to apply conservation of energy in the system. Conservation of mechanical energy, right, to the system. So you can see that during this time, going from here to here, and of course, wait a minute, this is wrong. The speed of the block, yeah. So by now the block has developed a speed v. Okay. So plus half mv square is the change in kinetic energy, minus mgs is the change in gravitational potential energy, and plus half kx square is equal to the change in elastic potential energy. This should be zero. So this is our second equation, which is coming from conservation of energy for the system. Okay. So we substitute this over here. So half mv square becomes mgs minus half k. Now x will become, as you can see, s by 2 whole square. So we have v square is equal to 2gs minus ks square by 4m. Okay. So that's how we get v as a function of s. It is square root of 2gs minus k by 4m s square, where g we will substitute as 10, k we will substitute as 50 into 10 raised power 2. So we'll substitute everything in SI units, and m we will substitute as 7.5 kg. S should be in meters, then V is in meters per second. No, I've divided by half m na beta on both sides. That's why I've got the 2gs term here, and this becomes k by 4m. Okay. Yes, Aman. Yeah, that will come in. Basically, we'll have to solve this for as a function of time. So we'll have to write the velocity as ds by dt and integrate for s with respect to time. So you'll get the displacement as a function of time. Okay, but that's a little bit complicated. I wish we will discuss that in a later chapter. Okay, simple harmonic motion. The time calculation of this type of question will be discussed in a later chapter, simple harmonic motion. Right now, we will discuss about the application of work energy. You will see that this actually oscillates up and down as a harmonic function, as a sine function. So this system now, once we release it, it's never going to stop. It's going to keep oscillating up and down. And every time it goes through the mean position, it will have maximum speed. And every time it comes back to the upper extreme or the lower extreme, the speed will reduce to zero. Okay. So work energy will help us determine those things over here, that what is the maximum displacement, what is the maximum speed, etc. but it will not help us in solving the time related part of it. Whereas the time related part of it, you have to actually basically go back to kinematics. You have to solve, this is v as a function of s, so you can replace v as ds by dt and integrate both sides. Okay, so you'll get s as a function of time, and when you do that, you will see that this is a harmonic motion, so s will be a sine function of time. So the displacement will be like a sine curve, it will be like a sine wave. It goes from 0 to maximum, then comes back to 0, then again goes to maximum, that kind of thing. Okay, so that will come in the chapter of oscillations later. Okay, we can do it right now, but the thing is, work energies application does not include that, so we are avoiding the time calculation. So anyhow, let's look at the substitution of the terms next here, so that we can find out the specific terms, maximum speed and this thing. Okay, so one is, so see, we have got this v as a function of s now. So one is that we can just rely on pure mathematics and we can find maxima of s and all that from this. Okay, so this is the first part done, first of all. Okay, now the second part, so this is the velocity as a function of time. Now for the second part, we want to find v max, want to find the maximum speed. Now we can see that in the above equation, v is some kind of function of square root of some function of s now, where that function is 2gs minus k by 4m s square. It's a quadratic function. It's like it's a quadratic function of s. So v max, just to make things simple, is square root of f max. We just want to find this function's maxima. So that's pretty easy. Now this is a quadratic function, so you can find its maxima quite easily. So let's do that next. So that is the easiest way to deal with this mathematically. That how do we find the maximum? You just observe that the function v is actually a transcendental function. It's square root of a function, and that function is what is a quadratic function. So it's very easy to calculate square root. So the function is this thing, 2gs minus k by 4m s square, where we can take s common. So this becomes 2g minus k by 4m s. So this is like that thing. So if you think of the function in terms of s, this will be this sort of a graph. It's a parabola with a negative coefficient. It's like a as minus bs square. You can see one root is 0 and another root is, so f is equal to 0 at s equal to 0 and s equal to 8 mg by k. This is like the first root alpha, this is like the second root beta. Okay, so in between the function, it's a parabolic function with a, okay, so it will reach a maxima at which point? At exactly the midpoint of the roots. Okay, so this should be alpha plus beta by 2, where this is your alpha, this is your beta. So it should be 4 mg by k. This should be the function's maxima. Okay, so I'm using that concept of theory of quadratic equations here. So if E is negative, that means it will be a parabola like this. Okay, and if it has some roots, alpha and beta, y is equal to 0 at x equal to alpha beta, then the vertex is always at the midpoint. And the vertex is where the function has the maxima. that becomes this point, the vertex. So I'm using that concept over here. So you can see that the roots of the equation are this and this. Okay. So the vertex is at x equal to 4 mg by k. Okay, so this tells me that this function is maximum at which value of s? At the value of s equal to 4 mg by k. Okay, so hope this is clear to all of you. This is making sense also. Okay. Good. Okay, so now we're almost done. We can just, so we know that the function is reaching the maxima or the vertex at this value of x. So function's maxima is nothing but the value of the function at s equal to 4 mg by k. So just substitute that over here. So it is nothing but in this function, you just substitute this. This function substitute the value of s as 4 mg by k. So this one become 4 mg by k into g minus g. Okay. So this function's maxima you can see will become 4 m square g mg square divided by k. So this function itself, its maxima. You can of course do all this after substituting the numerical values also, but here I find it more convenient to do it this way. Also because I'll be explaining to you the free body diagram also, so I want this reference. Okay, so the function's maxima is 4 mg square divided by k. So that means v's maxima is square root of the function's maxima. So according to this, the maximum speed we should get should be like this. It should be square root of 4 mg square by k. So k in the denominator. So this will in fact become 2g square root m by k. And we can then find out the numerical value of this. Now we'll substitute the values of m and k and g, and we'll get the numerical value of maximum speed. Next step. Okay. So just make a note up to this, people. We'll discuss further. So this little trick that I'm telling you now, making use of quadratic function and vertex of the parabola and all that, this is going to be very useful in this typical type of work energy questions, because wherever you have a spring mass system, you will see that your kinetic energy will always be a quadratic function of displacement. So always dealing with quadratic functions. So you want to put minimum effort in terms of solving. So don't get into calculus, differentiation and maxima and minima. You can just use the simple concept of the shape of the parabolic graph and the properties of the vertex and in terms of the roots and things like that. Okay, so this is very useful. See, we'll use it in a number of problems. Okay, so here now we should be getting the maximum speed's numerical value as square root of 2 into 10, 2 into 10 into square root of mass, which was 7.5 kg, divided by this. Okay. This is the maximum speed I am getting in meters per second. Yeah, Kevin, same value you have calculated numerically, is it? Yeah, that's correct. So that's correct. This will be approximately, we rounded off up to second place of decimal, it will be 77.77 meters per second. Okay, very good. So understood the concept here. No? Okay. Now I'll also show you this with a logical free body diagram kind of method. Okay, why the speed is becoming maximum at this value of s, 4 mg by k. This we have understood purely mathematically. How did we get that the speed is becoming maximum at this particular value of x? Okay, in fact, let's calculate this also. So we can see that this value of x is 4 times its weight. So 7.5 into 10 divided by the spring constant. Now this one we can substitute in newtons per centimeter, so that we get, so this will become, how much will this become now? Be 30 by 5 or 6 centimeters, right? It so appears that this maximum speed is at x equal to 6 centimeters. Now, why this is coming, that also we'll discuss in terms of free body diagram. Okay, one is, of course, we've understood this in terms of the mathematics, okay, that as a function it's reaching the maxima at that value. Okay, so not only we have got the value that the maximum speed is 0.77 meters per second, but we also know that it's reaching maximum speed at x equal to 6 centimeters. Okay, so let's for a moment go back to the diagram and also understand the free body diagram of the block and the relationship between the block's acceleration and the, or yes, very good, that's correct, Kevin. The maximum displacement is also correct. Okay. Okay. So as I was saying, let's also understand for a moment the relationship between the block's displacement and acceleration, and from that how we can determine the fact that at what value of displacement the block should reach its maximum speed. Let's try to understand that. So we take this diagram here and we try to understand the forces which are at play in this system. So you can also logically understand that why at x equal to 4 mg by k, we should get the maximum speed. So in this diagram, see that the tension the tension at any point of time is such that, make the pulleys free body diagram, remember it's massless. Okay, so net force on the pulley should be 0. So the spring force acting from above, Kx, should be balanced by 2p. Okay. So Kx is equal to 2p. That's one thing. Okay. And next thing, if you look at the block, does this. Okay. So if mg is greater than t, then mg minus t is ma, where a is plus of dv by dt, because its velocity is going down, as you can see right now. Whereas if t is greater than mg, then t minus mg is ma, where e will become minus dv by dt. So what this set of equations here tells us is that the block initially accelerates, because now you can see that there's a relationship between tension and displacement. Okay. So from this you can see that tension is equal to kx by 2. So that also means that tension is equal to ks by 2. Sorry, by 4. Because remember, s was equal to 2x. So this is the relationship between tension and displacement. So now if you connect this statement, you can see that acceleration is equal to plus dv by dt, that is speed is increasing when mg is greater than t. That means that s is less than 4 mg by k. That is a condition for this. So this thing, the speed is increasing when this thing is occurring, or s is less than 6 centimeters. Whereas e becomes negative, that means speed is decreasing when t becomes greater than mg. Or in other words, or s becomes greater than 4 mg by k, or s is greater than 6 centimeters. Okay. So this is what is showing us that now the speed starts decreasing when this happens. So in between is when the speed is maximum. Okay. So therefore, between this and this, at x equal to exactly 4 mg by k, or 6 centimeters, for a moment the acceleration is 0. Before that the acceleration was positive, after that the acceleration is negative. So that is when the speed is maximum. So this is the dynamics way of justifying that. The thing that we saw by the quadratic equation analysis, that we are justifying by the dynamics over here from the free body diagrams. Okay, so this is a very critical part of the analysis in a question like this. Okay, so hope this is clear, people. Now to move on to the last part of the question, the maximum displacement, that's very easy because the moment it reaches the maximum displacement, see what is happening from 0 to 6 centimeters, the block is accelerating, so its speed is increasing. Then the moment it crosses 6 centimeters, this one, again it starts decelerating, so the speed starts decreasing. So it will continue down with a deceleration till it stops, and wherever it stops only momentarily because it has an upward acceleration, and it will from that point again come up, and it will be like a mirror image of the downward journey. So it keeps going up and down between x equal to 0 and maximum, and in between is your x equal to 6 centimeters where the speed is maximum. So one thing is you can just do a shrewd guesswork that in any oscillation, the displacement from one extreme to the mean position is always the same on either side. So if you have to go down 6 centimeters from x equal to 0 to your mean position, and obviously from mean position to lower extreme, you have to go another 6 centimeters. So most likely the displacement is going to be 12 centimeters at the maximum position. But that you can also justify from work energy by applying the condition that the speed of the block or the kinetic energy of the system should be 0 at the lowest point. So whenever this block reaches the lowest point here in this diagram, its V should be 0 for that moment, for that instant. Okay, so that is the complete explanation of this. Yes, 8 mg by k from the graph. Correct, Nikita. We already made the graph, so we already have the solution in one sense because we know kinetic energy is becoming 0 at the second root, which is 8 mg by k, which will numerically be 12 centimeters. So actually, like you correctly pointed out, we have the answer already in the graph. We can see that the function is 0. That means kinetic energy is 0, no? Because the function is v square. So it's proportional to the kinetic energy. So basically, we have the answer here itself. We have the answer here. This thing, wherever this becomes 0, that is your S maximum. Okay, so we have this equation from before. So in this, you can see that the kinetic energy is this quadratic function. This has the same graph as that function. Kinetic energy versus displacement. We'll only draw that part of the parabola which has non-negative values of kinetic energy because kinetic energy can't become negative. Okay. So these are your roots. Okay. This is the midpoint of the roots. So you can see that kinetic energy is equal to 0 at S equal to maximum displacement. So while this completes the problem, but you can also observe one more very interesting aspect of the system here, and that is the symmetry of the oscillation. If you look at the symmetry of the oscillation, you'll understand where your system started out. At this position, x was 0, s was 0, u was 0. So at that moment, what would have happened is also that tension is zero. So it is starting with a maximum downward acceleration just at that moment of G. Okay. Now from here, when it reaches the position where the speed is maximum, okay, at that point of time, what would have happened is that our S was, okay, but more importantly, our acceleration would be zero. So this would be the mean position. Okay. This is the position where S was 4 mg by k, or 6 centimeters. Now compare this with the lower position, the lowest position, that is. Again here V becomes zero. Okay. So it will again have a maximum upward acceleration at this point of time. And you will see that maximum upward acceleration is actually equal to G. It's always symmetric, because at this position now, what is happening is our S was 8 mg by k. So at that position, if you look at the free body diagram, the tension was kx by 2 or ks by 4. So if you look at the tension at the lowest position, it's actually double the weight. 2 mg. So that is why it has an upward acceleration, okay, of this maximum tension at the lowest position minus mg, which comes out to be g upwards. So there's that symmetry. So if you just look at the block alone, it starts from this position with a downward acceleration of g. Somewhere in between, it has a downward acceleration, some velocity. Then it reaches this position where acceleration becomes zero. V becomes maximum. Okay, so this is when your S is 6 centimeters. Then as it crosses this, it's decelerating while it's going down. Then it reaches the lowest position where once again the acceleration becomes maximum, but V becomes zero. So it oscillates between this and this extreme position and this position, which is the mean position. It keeps going back and forth like this between these. Goes down, comes up, goes down, comes up. And every time it crosses this position, it has maximum speed. Every time it's at the highest or lowest position, its speed is zero. So this is the overall symmetry of the oscillation. No, see, that is the thing now. Unless there is some kind of dissipation of energy, like some non-conservative force. In real life, of course, there is non-conservative force. There is the air resistance, which keeps dissipating the mechanical energy of the system with every cycle. So even when it's oscillating, with every cycle of oscillation, the amplitude reduces, and eventually it comes to rest at the mean position. But in a very idealized situation where we can neglect air resistance. So for example, if we conducted this experiment in a vacuumized container, okay, with a nearly ideal spring, which doesn't dissipate any energy, then this would be perpetual motion. It would oscillate forever, like a perpetual pendulum. In fact, that's how mechanical pendulums work. Na? There is some dissipative element, but that is minimized through a mechanical system which is very elaborate. And to compensate for the energy loss over time, some kind of mechanical energy is given to a spring mass system. That is the winding of the clock in the case of mechanical clocks. Or in modern day mechanical clocks, which are Swiss made and all, it is compensated for by the kinetic energy of the clock itself, when it's moved around. So you don't have to separately wind the clock. But if you've seen olden day clocks, grandfather clocks, etc., yes, because of the law of entropy, I use that's correct. So there is always dissipation of energy happening in the universe. Okay, but it can be minimized such that it becomes negligible. So it is possible to have a mechanical system where you have reduced the dissipation so much that this thing might be oscillating for years before it eventually comes to rest. And of course, if you're taking the idealized situation like we're taking in our calculations here, it should oscillate forever without ever stopping. So what all that is happening here is conversion of kinetic to potential and potential to kinetic energy. So if you think in terms of energy, what is happening here is that also visualize energy versus displacement graph. So in that, if you look at the kinetic energy versus displacement we've already seen is like this. It's peaking at the mid position of 6 centimeters and again becoming 0. So now if you look at the potential energy, now how will we define the potential energy? We'll have to define the potential energy as the sum of gravitational potential energy plus elastic spring potential energy, where we will take the potential energy at the top. Suppose we take that as 0. We take that as 0. So gravitational potential energy at some displacement s will just become u naught minus mgs, or we can take that as just minus mgs. So if you look at the gravitational potential energy, it is minus mgs. Okay, so this is minus mgs plus half kx square, where s is by 2 like this. So if you look at this potential energy function and you actually plot that function, you will see it exactly fits like this. Exactly fits like this. And therefore the mechanical energy, the total mechanical energy of the system, that is the sum of kinetic and potential, it will be constant. The mechanical energy is constant, while the potential and kinetic are, so your system keeps going back and forth between this. It goes back, forth like this. And every time it's going back and forth, kinetic is converting to potential, potential to kinetic, kinetic to potential, and like that. So in any kind of oscillation, that is always happening. Maximum stability is at the position where potential energy is minimum. So you can see again that your potential energy graph has the local minima at the mean position. Potential energy has local minima at s equal to 6 centimeters or 4 mg by k. So this is the stable equilibrium position. So that is why if we allowed it to drop very slowly to the equilibrium position and released it, it would remain in equilibrium forever. And any small displacement given from the equilibrium would result it in coming back to equilibrium because there is restorative force. But here, because we have released it from much higher up, so by the time it's reaching equilibrium, it already has kinetic energy. So it goes past that equilibrium position. But the internal force of the system, it always tries to bring it back to equilibrium. So you can see on acceleration on either side of the equilibrium is pointing towards equilibrium. Now, when you're above that 6 centimeter mark, your acceleration is pointing downwards. When you're below the 6 centimeter mark, your acceleration is pointing upwards. So the direction of the net force is always restorative. So again, it's a stable equilibrium position. There's a local minima of the potential energy graph. So you can see through this one example, you learn a lot of aspects about mechanical systems which have conservation of energy happening. Okay, any kind of spring mass system or combination of vertical spring mass system. So gravitational potential energy is combined with spring potential energy. It will be some kind of function like this. Now the constraint relation might make all these factors differ, whether it is 1 by 8ks square or 1 by 16 or 1 by 2 or whatever, but the form will always be quadratic like this. And the concept will always be the same, that there is a mean position in between, and in the vertical system, the highest position and the lowest position, those are the positions where the kinetic energy is zero. So the overall potential energy is maximum. Because you can keep coming back to this one example. Whenever you're dealing with the vertical spring mass system, the only thing that will change is the constraint relation, depending on how the spring is connected. If there are multiple springs, then that can be another case, things like that. Okay. At some stage during work energy, we'll also discuss about a combination of springs and also cutting of a spring. That if we cut a single spring, how we can determine the spring constant of the individual pieces that we get. Like if you cut a spring in exact half, then you get two identical springs which have double the spring constant. But if you cut the spring in some ratio of length, then there is a particular method we use to calculate the individual spring constants of the individual pieces that you get. So that also we'll be discussing at some stage. Okay. Now let's come to another important example of application of work energy theorem. Now this example itself is also going to be like a theorem for us. Okay. So in this particular example, what is happening is that, let's say we have a situation like this. So certain vertical height h and a certain horizontal displacement d, but joining the 2 points is an irregular kind of curved surface. Okay, so this is an irregular rough surface. It's a rough incline, but not a uniform inclined surface. It's an irregular inclined surface. Irregular slope kind of thing. So coefficient of friction is mu. And from this position here, a particle is released from rest. So it's going to slide down and eventually reach this position B. And we want to find the kinetic energy by the time it reaches B. So particle mass m is released from rest at the point A. So first of all, we have to calculate the work done by kinetic friction on it as it slides down from A to B. And then we also want to find its speed at the point B. When it reaches the point B, how much is the speed going to be? Okay, so just try to figure out, how we'll set up the work energy thing here. Then we'll discuss this question in detail. Okay, you have to just be careful of the algebraic sign, but of the work done by friction. Ayush, your answer is almost correct, but be careful of the algebraic sign. Yes, now it's correct. Okay, so let's understand this question in detail. So the thing here is now we have to understand the like an instantaneous free body diagram at some point of time for this. So we have to understand a situation something like this, that at some instant if the particle is at some intermediate position, between A and B, and it makes a differential displacement. How do we deal with that? Okay. So this particle is somewhere here at some stage. Okay. And from here, it is making a differential displacement like this, a very small differential displacement along the instantaneous tangent. It's making a differential displacement ds like this. Okay. So that is along the tangent to the curve at that particular point. Now, about the forces acting on the particle at that instant, the forces are going to be mg, which is vertically downwards, and normal reaction, which is acting normally to the curve, and kinetic friction, which will be acting tangentially backwards, opposite to the displacement. So this will be our kinetic friction, this will be our normal reaction, this will be our mg. And you can see that this is the tangential axis, this is the normal axis. Okay, like this. So if this angle is theta at this point of time, you can see that normal reaction's instantaneous value will be mg cos theta. Therefore, kinetic friction's instantaneous value, which is mu n, will be mu mg cos theta. Now, the other thing you can also see in this diagram is that if you take your x and y axis to be horizontal and vertical instead of along the incline and perpendicular to the incline, if you take our x and y axis to be horizontal and vertical, then at this point of time, the displacement vector ds, what kind of angle it's making with the x axis? It's making an angle of theta. So that differential displacement, that vector is like this, no? So it is along the tangent, perpendicular to the normal. So with respect to our x and y axis system, you can see that this angle was theta. So this angle is theta. So we can write that differential displacement as dx I cap minus dy j cap, where dx will be ds cos theta and dy will be ds sin theta. Okay. So this is the instantaneous picture. So ds is the instantaneous displacement in a very small time dt. At any point it is along the instantaneous tangent. So this is what is going to help us calculate the work done by friction, that part of the question. So during this small displacement or during this small time dt, the work done by friction will be kinetic friction's dot product with displacement. So that you can see is minus kinetic friction into ds. So that is minus mu mg cos theta into ds. Okay. So you can see that actually becomes minus mu mg ds cos theta. These two terms you can put together here. So that is actually minus mu mg dx. So this work done by friction during that small displacement is actually this term, but it can be reduced to this term. So total work done by friction from A to B will just become integration of minus mu mg dx from A to B. So that is nothing but the change in x coordinate from A to B. That is nothing but d, as you can see, the horizontal component of displacement, d. So that's how this question is ultimately solvable, even though the curves equation is not known to us. So it looks like a very complicated situation because the path is complicated, but it becomes solvable. This becomes minus mu mg into the horizontal component of displacement. This is our work done by kinetic friction from A to B. So this is the solution of the first part of the question. Just make a note of this and discuss with me if there is any confusion or any point you want to talk about in this. Okay, now for the second part, we can see that work done by normal reaction is 0, because at the same time, just like we've calculated work done by friction here, if you see work done by normal reaction is always going to be perpendicular to the instantaneous displacement. So that kind of situation we have discussed before also. So you can see also here that work done by normal reaction, which will be n dot ds, will be 0, because n is perpendicular to the instantaneous displacement at all points. Okay. So that is what is going to help us work out a second part of the question here. So we can see that ultimately work done by friction will be the change in mechanical energy. Yes, that's correct, Kevin. So we get a sort of a formula here. It should be change in kinetic energy plus change in gravitational potential energy. Or you can even say that work done by friction plus work done by mg the combination of work done by friction and mg is equal to the change in kinetic energy. It's one and the same thing. Okay, because you can see that delta U is nothing but negative of work done by gravity. Okay, so either way you can see, so this is very easy. So this is, we have seen minus mu mg t. This is going to be plus half mv square because it started from rest. Okay, because U is equal to 0 at A and V is equal to V at B. Okay, minus mg h, because you can see that change in the vertical coordinate is minus h. So delta U for gravity, we use this formula. So from this we can see that we will get the equation for the kinetic energy as this. Okay. So V will come out to be square root of 2g h minus mu t. So you should, in a sense, remember the result of this particular example like a theorem. When you have an irregular rough slope of coefficient of friction mu, this is the way to calculate the work done by friction. Now, this is the way to calculate the speed after it has dropped through a height h, while it has traveled a horizontal displacement of d. Okay, so hope this example is clear. Now, one more point I'd like to add over here before we move on, that when you look at the expression of work done by friction, here you can see that work done by friction from A to B, it is minus mu mg into xb minus xa, that is minus mu mg t. It appears to be path independent. Okay. Which is correct also, it is path independent. However, we cannot say here that friction is acting like a conservative force, because the other very important condition for a conservative force that is that in a round trip, the work done by friction should be zero. But here, for example, if you allow the block to slide from A to B and then you push it back from B to A, so the whole round trip, will the work done by friction be zero? No, because kinetic friction cannot do positive work. Even on the way down, it's dissipating energy. Even when you slide it back up by applying some force on the block, whatever work kinetic friction does, it will be doing negative work, because its direction will always be opposite to ds. So the net work done by kinetic friction in a round trip will be a negative quantity. It will be a non-zero negative quantity. So while in this particular case, when it's sliding from A to B, it appears that the work done by friction is path independent, but it is not overall path independent, because in a round trip, it's not going to be zero. So friction is not acting like a conservative force here. Friction is still acting like a non-conservative force, because the stronger condition for non-conservative force is that it should always do zero work in any round trip. But here in any round trip, the work done by friction will be negative. Even if you allow it to slide back to B and then pick it up from B and place it back at E without coming in contact with the surface, even that's a round trip. But the net work done by friction in that round trip will remain negative, because in your second part of the journey, where it's not in contact with the surface anymore, friction is not doing any work. So whatever type of situation you imagine, if you're making a round trip from A to some other point and back to A, the work done by friction cannot become zero in that. If it's kinetic friction, it will be negative. So it has to be a non-conservative force. So this is very important to keep track of, that. A closed loop type of path back to A will always be non-zero. In fact, it will be a negative non-zero quantity. So friction is a non-conservative force. Kinetic friction is acting as a non-conservative force. So always, without exception, actually kinetic friction acts as a non-conservative force. Okay, so these are a couple of additional points about the application of work energy theorem that I wanted to discuss with you. We have been doing this type of situations with constraint relations and all that in the last couple of lectures also. So just add this to those set of questions. Now we will go back to a little bit about the analysis between potential energy and internal conservative force, and again the theory of conservative forces and things like that. And we will do that today in context of a very important type of force called central forces. So we're moving on to slightly more advanced things with respect to a JEE syllabus now. We are moving into types of application of work energy which are going to help us in future chapters like gravitation and electrostatics, and also for more advanced level questions at the JEE advanced level. The basics of work energy are more or less done. Still have to discuss about power though. Right. So next we will talk about a very important category of forces called central forces, which is a special type of force in physics which we come across very often in terms of the fundamental forces. So this is like a certain category of forces seen in physics overall. Fundamental forces of gravity and electrostatic force, including Coulombic force. The Coulombic attraction or repulsion between opposite or like charges are examples of this category of forces. So central forces are given by a general formula and a general principle about how they act. Okay, so here we are talking about a general three-dimensional coordinate frame. So in an XYZ system, if at a given point or if at a given position P for a body or a particle, a force acts on it in such a way that the force is related to its position vector R. Is the force is related to its position vector. This is not a continuation of the z-axis. So the force acting on this particle is somehow related to its position vector by this particular formula, which I'm putting up next. At a position vector, at an arbitrary position vector given by some x I cap plus y j cap plus z k cap, a central force acting on a particle will be given by the general equation this. Okay. So this is the general formula or general expression of central force, where alpha is a constant, can be negative or positive. R is of course magnitude of the position vector, and R cap is the unit vector along OP, where O is the origin, or unit vector of the position vector R. Okay. And N is any real number. So this is the general formula of central force. Yeah, when the value of N is 2, then you have that particular example of Coulombic force or gravitational force, K Q1 Q2 by R square. But the whole point is central forces is like a general family of forces where the value of N need not be 2. N can be, for example, half also. N can be minus 2 also. Okay, so basically the magnitude of the force should depend on some kind of power of R. And the direction of force should be either along plus R cap or minus R cap. In the example that I have shown, it is repulsive with respect to the origin in the diagram. So the alpha must be a positive quantity. But alpha can be a negative quantity also, in which case the direction will point towards O. rather than repulsive away from O. Okay, so this whole general family of functions or this category of forces together is called the central force. And Coulombic force, which we have seen as a formula, or the universal gravitational force, capital G m1 m2 by r square attractive force, these are just special examples of central force. But there are many other examples. Okay. Okay, so what this basically says is that the magnitude of any central force should be proportional to some kind of power of r, or magnitude of f is equal to alpha upon r to the power n. Example, Coulombic force, where the magnitude of the force is k q1 q2 by r square. Okay, so you can see that the magnitude of the force is proportional to r to the power minus 2. Okay, and the direction of f is along either plus r cap or minus r cap, depending on whether alpha is positive or alpha is negative. So this is the general category of forces, central force. Why this is important for us is because next thing we'll see that as a rule, all central forces are conservative, and we'll just look at the proof of that very soon. And we'll develop a general formula for potential energy of any conservative force, sorry, of any central force. Now, next thing very important about central forces. Central forces are conservative by definition. Okay, and let's understand the proof of this. So the proof lies in the path integration. Now let us say we are taking a body from this position A to this position B by some kind of path like this. So Yeah, Tanishq and Amog, I'll take you back to that slide above after I finish with this. Okay, so just let's look at this for a moment. Okay. So a particle is moved from A to B via a path shown, while a central force F acts on it. So at some intermediate point of time in between, if the position of the particle, at some in between time was here, this is where the particle is located at some time t at a position vector r. Okay. And it makes a very small displacement along this path ds in a small time dt. So you can see that the central force that is acting on it will be doing a certain amount of work. So we assume that force is along this vector. Okay. So during time dt, okay, the work done by this central force F dot ds. So that will be whatever constant divided by r to whatever power into r cap dot ds, this kind of expression. So the total work done will be integration of alpha upon r to the power n into r cap dot ds. Okay. Now if you pay attention here, r cap is the unit vector along r. Okay, so therefore r cap dot ds will become nothing but ds cos theta, where theta is this angle. It is the angle between the unit vector r cap, which is the same as the direction of the force, and the differential displacement ds. So this is nothing but dr. Okay, that is the component of the displacement along the radial unit vector or along r cap. Okay, so r cap dot ds, this whole complicated thing, can be reduced to something very simple over here. It is the small change in r dr. Okay, when the body is moving by some ds, it causes some change of position with respect to the origin. So the magnitude of that change in position is dr. So that is nothing but r cap dot ds. So next step, this reduces to alpha dr divided by r to the power n from a to b. So we are calculating the work done from a to b. So now you can see that this becomes an integration which is independent of the path. Okay, this is an integration of just this from a to b. So it will be alpha into r to the power minus n plus 1 upon minus n plus 1 from a to b. So when we substitute this a and b next, you can see that the value of this integration is going to be independent of the path. It is only going to depend on initial position A and final position B, which is the general proof that the central force is conservative in nature. Okay. So you can see that this we can also write like this. One upon r to the power n minus 1. Just bring this to the denominator from A to B. So it is alpha upon minus n plus 1 okay, into 1 upon position at B to the power n minus 1 minus 1 upon RA to the power n minus 1. So you can see this is independent of path. It only depends on initial position and final position. And also that in any round trip, if you're coming back to A, then your RB will be equal to RA in this expression. So by definition, your work done will be 0. So it shows that the central force by definition is conservative. Now, whether that value of capital N is 2 or 1 or half or whatever it be, it will always be conservative in nature. So next step, we'll see that this expression shows us that it is a path independent term. The work done by this kind of central force is path independent, and in a round trip, the work done will be 0 always. So that is the proof that all central forces are conservative. Okay, so next up we'll see from this that this implies that the work done is path independent. Okay, and work done will be 0 for any round trip or closed loop kind of path. So this is what confirms the fact that central force in the above expression F are conservative. Yeah. So I'll just take you for a moment to the previous slide. Some people had to write down this part. Yeah, formula of central forces, Javel, that's correct. It is, it's basically a category of forces, and the formula is developed from observation of this category of forces. Okay, that the force is, the natural thing about the force is such that it's a fundamental type of force like electrostatic force or gravitational force, which acts in such a way that its direction is always either along plus or minus r cap, and its magnitude depends on some kind of relationship with r, whether that is 1 by r square or 1 by r or 1 by square root of r or whatever. That depends on the type of force we're talking about, the exact force we're talking about, but it depends on some kind of power of r. And at the same time, the direction of the force is either repulsive plus r cap or attractive minus r cap towards a fixed point, which we take as the origin of the system. So this is from observation of so this is from observation of actual forces, fundamental forces, right? Okay, so let's look at an example in this context before we wind up today's session. So now, why I'm explaining all this over here is because one, though you will be encountering these forces in chapters like gravitation and electrostatics in future in class 12. The second is you can always get a question like this one, which I'm showing next, which can be solved very easily by understanding and recognizing that it's a central force. Okay. So suppose we have an example like this, that for a particle in a 2D motion, moving in the xy plane, a force F given by acts on it at position x comma y. Okay, just a moment. Just give me a moment, guys. I'll share the file again. Yeah, so this type of force acts on it at a position xy. Okay, so first of all, calculate the work done by this force from, let's say, position A Okay, so this kind of expression, let's look at it. So there are a couple of ways by which we can approach this question, which is what we'll discuss next. One is we can go with a very standard kind of approach that we have taken till now, that we try and do the path integration by using calculus. So the first approach we can take is we just calculate the work done by integrating f dot ds, substituting ds as dx I cap plus dy j cap. Okay, so this work done becomes now dot product of this force, which is so just substitute this dot product here and you will see you'll get something like this. So now if we are calculating the work done from A to B, substitute accordingly. Now the thing is, how do we integrate? So it's a matter of observation here that x dx plus y dy is nothing but half the derivative of x square plus y square. So in other words, suppose we take then dz so we do this substitution here. This is a substitution we do in the integration. So on doing the substitution, you can see that this becomes 2 alpha, oh sorry, alpha by 2, mistake, dz divided by z, okay, from A to B. So it becomes alpha by 2 ln z from A to B. Then we substitute z back over here. So it becomes alpha by 2 ln of x square plus y square integrated from A, which had the coordinates 3a comma 4a, to B, which had the coordinates 8a comma 6a. So this will become natural log of 64a square plus 36a square minus natural log of 9a square plus 16a square. And you can just complete this calculation next. So you can do ln A minus ln B is ln A by B. So this will become 100a square divided by 25a square. Okay. Or this is the final answer. Just do one more step here. Okay, so this is sort of a fundamental way of doing the question. And as far as the second part is concerned, from this step itself, you can see that the work done is independent of path. From, in general, if we calculate the work done, it is alpha by 2 from whatever initial position, whatever final position. So you can see that this expression is path independent. Okay. So therefore, the force is conservative. Okay. Now another way of doing the same question, we'll see, is that we can convert this to use the radial system where the position vector is xi cap plus yj cap. So the magnitude of the position vector is this, and r cap nothing but r upon r. So now you can see that the given force in this system, it is nothing but this. Okay. So the force is nothing but alpha r cap by r. So it is a central force. Okay. With this thing, with our n equal to 1. So therefore, it has to be conservative. Okay. And then we can use the same derivation for work done by central force that we done earlier to calculate the work done. Okay, so as you can see, this will become So it is alpha ln r from A to B. Okay. So at A, at B, so this will just become, and then you substitute all this, so you get okay. Okay, so people will conclude here today. We'll pick up the second part of this question in the next lecture, where we are developing the formula for potential energy. But for that, we'll just use the relation that delta U is negative of work done by internal conservative force. So here, this is that central force. So we will see that our potential energy will become an ln R type of term. We'll have ln R type term. So we'll discuss about that in the next lecture. I have a lecture coming up next. Okay. But hope you've understood the. Yeah, actually, Ayush, the module has more variety of questions than HC Verma. Okay, so HC Verma is good for the basics and the applications of work energy theorem. But when it comes to all this conservative forces and potential energy concept and uh, more advanced things like the gradient operator and all that we discussed in the last lecture, your module will help you more. So if you've done the module, if you've prepared the questions from the modules, then you're in a very good position for the major test coming up. Even if you've not done the module fully, but you've completed HC Verma and most of the questions of the module you're confident with, you should be in a good position for the upcoming test. Okay. So next couple of lectures, we'll be discussing more questions and doubts. Theory wise, we are really done with work by energy. Okay. So in the next lecture, please be prepared with any doubts that you have from HC Verma or from the module. Okay, we will discuss both. So that's it for today's session, people. Wish you all the best. And once again, Happy New Year for 2021. That's it for today.